Everyone, this is Mr. G. All right. What I want to do today is I want to go over this quiz, this 10-question quiz that we had on shape and porosity and the relationship between shape and porosity and those things. Okay. I got some of the responses back already, and I was a little disappointed. I was hoping for slightly better grades on this one, but that's okay. That's all right. It's this is a tough way to learn, so that's all right. Let's go over these questions actually one by one. There's only 10 of them, and so we should just do each one and we'll understand. All right. So name. I'm gonna do it like as if I'm taking the test myself. Right. So name. I'm gonna go ahead and put Mr. G. All right, and my email over here is Dan dot Jimenez at mcmail.org, mcmail.org. Okay, mcmail.org. Okay, let's do the first question. All right, ready? Okay, so it says here, can I zoom in a little bit? No, I guess that's okay. It says here, all right, first question. The cross-section below represent 3 beakers that were used to test porosity. Okay, that's the relationship, the ratio between the size of the pore and the size of the particle. Beakers A, B, and C each contain a different size bead. Each beaker holds an equal volume of beads. The amount of water needed to fill the total pore space between the beads in each beaker was measured. All right. Now we did this one already in my last video, but just to recap. Which statement best describes the porosity that was found for for these 3 samples? Well, remember, same shape, same porosity. Remember, it's a ratio between the size of the pore, the space, and then the size of the particle. Well, small particle means a small pore, medium particle means a medium pore, right? And a large particle would mean a larger pore. So the ratio is the same. Therefore, the answer would be D. All 3 samples have the same porosity. Why? Same shape, same porosity. Okay, so the answer should be, nope, I'm sorry, D right there. Okay, next one. Zoom out a little bit on this one, can we? No. All right. So it says here the diagram below represents 2 columns, A and B, that we use to determine the infiltration rate and water retention of 2 different particle sizes by pouring equal amounts of water through each item. Okay. So we have here A, we have small pebbles and a screen. Here we have sand, and we know that sand is smaller than pebbles, right? Okay. So here, let's look at the question. Compared to column A, column B had let's see, column B is the one with the small particles. Column B had higher infiltration and retained less water? No. Smaller particles means less infiltration, right? Lower rate of infiltration, good, yep, because it's smaller, and retained less water? Well, small particles hold on to or retain more water than big, so I don't think it's B. Let's take a look at C. Low rate of infiltration? Yes. And retained more water? Yes. Because it's smaller, the sand, the water will infiltrate much more slowly through B. And also because it's smaller, B, right, the particles, that means it's going to hold on to more water, better capillary action, better capillarity, right? So it is, answer should be C. Next one. Number 3. Which type of sediment sample normally has the greatest permeability rate? Now remember, permeability is the ability for the soil to allow water to go through it. Good permeability or good permeable soil means good infiltration, right? So let's see, unsorted sand. So that'd be sand that has different sizes. No. B, sorted pebbles. Okay, so pebbles that have the same shape and size. Okay, yeah, maybe because it's bigger than sand. Sorted sand. No, because sand is still smaller than pebbles. So pebbles are still more permeable. And unsorted pebbles. No. So the answer here is B, sorted pebbles. sorted pebbles because they're all the same shape and size, right? And pebbles is bigger than sand, therefore it will be more permeable. All right, number 4. Base your answer to the following question on the diagram below, which represents samples of soil and bedrock at Earth's surface. Okay. The arrows represent possible infiltration of rainwater. Okay, so rain is coming down and going through these here. Okay. So the question is, which sample probably has the greatest porosity? And I remember porosity is the relationship or the ratio between the pore size and the particle size. Okay. Well, it says which sample probably had the greatest porosity. Well, let's see. These here have some pebbles in the middle and some sand. So it's unsorted, so that wouldn't be it. We have this granite where they're all locked together, so no, that's no good. We have these here. This flat shape kind of squeezes out any of the air. So it looks like it's this one here, the pebble soil. So the answer would be the A, pebble soil. That would have the greatest porosity. Because look at the size of the pores, right, compared to the particles. They're big, right? Bigger than any of the other choices. Okay, number 5. Base your answer to the following question on the diagram below and on your knowledge of earth science. The diagram represents setups of a laboratory experiment labeled A, B, C, and D. This equipment was used to test the infiltration rate and water retention of 4 different particle sizes. Each column was filled to the same level with uniform sized dry spherical particles. Okay, so each one of them are round. Okay, some of them are different sizes though, obviously. Water was poured into each column until the water level rose to the top of the particles. Then a clamp was opened to allow water to drain into the beaker beneath each column. All right, so basically what they did was they filled each one of these with round beads. These are larger round beads. These are smaller round beads, right? A is the smallest round bead. D is the largest round bead. Then they filled it with water and then let it drain out. Okay, so the question is, which column of particles retained or held on to the most water after the clamps were opened and the water was drained into the beakers? So what would hold on to more water? Big particles or small particles? Small particles, good. So the smallest particles are A, so column A, so choice D. Look how they tried to trick you there, right? Typical Regents question. Even though A is not column A is column D, right? So column A is actually choice D. They tried to trick you there, right? So we got to be careful with that. All right, that's an unfair question. I don't like the way they do that. That's not cool. But we just got to be more careful, right? All right, now the next one, number 6. Base your answer to the following question on the diagram below and on your knowledge of earth science. The diagram represents 3 tubes, A, B, and C, each containing an equal volume of uniform-sized spherical beads. Okay. The bottom of each is covered with a wire screen, X and Y. That's the reference line. All right. These tubes are placed in water up to the level of XY. All right, so they dip them into water until it reaches the level of XY. All right. To demonstrate the capillarity. After 1 hour, the height of the water above XY will be, well, let's see, the highest the water goes, right, will be the same for all 3? No. Remember, smaller particles, good capillarity, right? So, no, it won't be A. How about B? Highest in tube B. This is tube B here. I don't know. Tube A is smaller. This one should have better capillarity. Let's see if that's a choice. Highest in C? No, because those are big, right? Highest in tube A here. Yes, it would be highest in tube A because tube A is the smallest size particles. Okay, so it would be highest in tube A, so it's choice D. Down at the bottom, choice D. Okay. Number 7, almost done. The diagram below represents the 3 identical beakers, A, B, and C, each containing an equal volume of uniform-sized spherical beads. Okay, just like the other one. Water was poured into each beaker until all the pore spaces are filled. Okay. Which table best indicates the percentage of pore space compared to the total volume of each beaker? All right. Basically, they just gave you the definition of porosity in the question, the amount of pore space compared to the size of the particle or the volume of the particle, right? Because Volume is space, how much space something takes up. That's volume, right? You remember that from Earth Science 1, 2. Well, same shape, same porosity, right? Well, if the porosity has to be all the same, which answer, A, B, C, or D, has the porosity all the same? Percentage of pore space? A. Choice A. The porosity is all 40. They're all the same. Choice A. Okay. Let's move on to number 8. A soil sample with a high percentage of open space between the grains must be, okay, so soil with a lot of open space in between each particle, each grain of soil, that's the pore, has what? Well, is it porous? Yeah, well, porous means that water can go through it, like permeability, very porous. Have low permeability? No. If it has a high percentage of space in between, it would have high permeability. Have mixed grain sizes? Well, no. Because remember, if it's unsorted, mixed, right, different ones, it fills up the pores, so it would have small pore sizes. D, show high amounts of capillarity. Nope. Can't be that either, because remember, small particles make small pores, good capillarity. So it must be choice A. All right, almost done. Number 9. The diagram below shows an experimental setup to compare water retention and permeability in 2 columns with equal volumes of spherical plastic beads of different diameters. Okay, so this one here on the left has column containing 4 millimeter beads, right? And then the one on the right over here has 12 millimeter beads, so they're larger. Okay, so let's look at the question. Which statement best describes the water retention, hold on to water, right? Capillarity, holds on to water. Retention, holds on to water. Describes the water retention and permeability in the 2 columns of beads. So they're asking 2 things, permeability and capillarity, water retention. Well, let's see. The answer would have to be that column A has good capillarity, right, but bad permeability. And the other column, the one on the right, that one would have to be good permeability, but bad capillarity or water retention. All right, so let's see. Choice A. The column with 12 millimeter beads has greater water retention. No, because it's larger, has less water retention. Larger beads, less water retention. B. The column with the 12 millimeter beads has greater water retention and nope. Again, it should have less water retention, right? C. The column with the 4 millimeter beads has greater water retention, yeah, because it's smaller, good, and permeability. No. Because they're smaller, good water retention, yeah, but not good permeability. Let's look at choice D. The column with 4 millimeter beads has greater water retention, good, and the column with the 12 millimeter beads has greater permeability. Yes, that is true. D is the most correct statement, is choice D. All right. Now number 10. Base your answers to the following question on the diagram below, which shows 4 tubes containing 500 milliliters of sediment labeled A, B, C, and D. Each tube contains well-sorted, loosely packed particles of uniform shape and size, and is open at the top. Okay. The classification of the sediment in each tube is labeled. All right. So we have silt. We know that silt is the smallest. All right. Then column B is fine sand. So that's small particles of sand. Okay, which is bigger than silt. Then we have coarse sand, which is big sand, right? So far it looks like it gets bigger and bigger as it goes towards the right. And then the last one is pebbles. Okay, so pebbles is the largest. So A is the smallest, D is the largest, and it gets bigger and bigger and bigger as you go. All right, let's look at the question. Each tube is filled with water to the top of the sediments, and the tube is covered with a fine screen. The tubes are then tipped upside down so that the water can drain out. Okay, so they fill it up, put a screen on it, flip it upside down, let the water come back out. Okay. In which tube would the sediment retain the most water? In other words, in which tube would the sediment hold on to the most water? Well, we know that capillarity or capillary action holds on to water, right? Well, which one is the smallest? Silt. Good. Silt. So silt would hold on to the most water. So column A is A here, so it's choice A. Okay. Now let's submit and see what my score is. Let's view my score. I'm nervous. I hope I didn't get any wrong. 90. Uh-oh. Where did I make a mistake? Let's take a look. I must have made a mistake someplace. Well, right here. It says the diagram below represents two columns, A and B, that we use to determine the infiltration rate of water retention of two different particle sizes by pouring equal amounts of water through each column. Okay. Let's look at the question here. It says here, compared to column A, column B has lower rate of infiltration. Column B has lower rate of infiltration. That is correct because it's smaller, lower rate of infiltration. And retained less water. Looks like I made a mistake on the answer key. The answer is C, like I chose. I chose C. Lower rate of infiltration and retained more water. Less water can go through, and it held on to more of it because it's smaller. So I'm going to have to fix this answer key. All right, I'm going to have to fix this answer key, but it should be C, not B. Okay, everything else is correct, though. All right, so review this video one more time in case you're a little confused, and I'll fix the answer key right now. All right, talk to you later, guys.